Okay, so welcome back. And now what we're going to do is we're going to talk about derivatives and continuity because there is a relationship between the two. So it turns out that if a function is differentiable at a point, then it is also continuous at that point. Okay, now be careful. Doesn't go the other way around. Just because a function is continuous at a point doesn't mean that it is necessarily differentiable at that point. In fact, it may not be differentiable at that point. Okay? So this only goes one direction. So this is an implication. If the function is differentiable at a point, then it must be continuous at that point. And that's the focus of this theorem. So Theorem 1 says differentiability implies continuity. Okay, so that means it goes this way. If this, then that. So let f of x be a function and a be in its domain. If f of x is differentiable at a, then it is continuous at a. Now here's the proof. Now what we need to show, to prove this theorem, is we need to show that the limit as x approaches a of f of x is equal to f of a. That's the definition that we use for continuity, right? The limit as x approaches a of f of x is equal to f of a, right? So let's do that. Okay. And we're also assuming that f of x is differentiable. So let's assume f of x is differentiable. Okay? So let's do the limit. Let's take the limit as x approaches a of f of x. So again, we want to get to f of a. Now here's the thing. We're going to have to do, I'm going to do some manipulations here because I need to bring in the derivative, right? I have to bring in the derivative, okay? So the first thing I'm going to do is I'm going to add 0 to this thing. So how am I going to do that? By subtracting and adding f of a, right? So I'm building the quotient, the difference quotient. So now what I'm going to do is that's going to equal the limit as x approaches a of f of x minus f of a plus f of a. So I didn't change anything. All I did was add and subtract f of a. Okay? Now what I'm going to do is separate this out. So I'm going to write this limit as x approaches a of f of x minus f of a. Now what I'm going to do is I'm going to multiply the top and the bottom by x minus a. So I'm going to have x minus a here, and I'm going to multiply by x minus a out here. But I'm still going to have this plus f of a out here. Okay, so all I did was I grouped this together and I'm multiplying the top and the bottom of this by x minus a. Okay? Now, what I'm going to do is I'm going to use my limit laws. Okay? Okay? And so, what do I get? Well, now I'm going to distribute the limit by using limit laws. So now this is going to equal the limit as x approaches a of f of x minus f of a divided by x minus a times the limit of x minus a, so the limit as x approaches a, that's 0, a of x minus a, and then plus the limit as x approaches a of f of a. Now, this is the definition of the derivative, right? So this is f prime of a, right? That's the definition of a derivative at a point A. So that's f prime of a. Now, what about this limit? Well, what happens to this limit as x approaches a? You get a minus a, which is 0. So now you get f prime of a times 0 plus, and then what happens to this? Well, this is just a constant, right? If you're evaluating a function at a number, a real number, you're just going to get a constant, and the limit of a constant is a constant. So this is just going to be f of a. Well, guess what? This times this is 0 plus f of a gives you f of a. And we just showed that it's continuous at a by using the definition of being continuous at a point. And so therefore, since f of a is defined and the limit as x approaches a of f of x is equal to f of a, we can conclude that f is continuous at a. Okay? So therefore, okay, since f of a is defined and the limit as x approaches a of f of x equals f of a, f of x, how do we do this? F of x is continuous at a. That's the end of the proof. Always got to have your conclusion. Have a great day.